So I'll start. What was that in progress? Okay.
So came up with the idea. Hello.
We got a little feedback.
Oh,
Okay. So now. It's all right. Oh. Except I'm not seeing I got it on mine. Where's that coming from? Good. Oh, you've got it. It's on yours. Okay. Okay, good. Okay, so we'll pick back up again. So imagine for a moment, so there's no money, right? We all know what happens when there's no money, right? It goes to barter. We tend to have this idealistic concept of barter, that it's this really nice thing with no money. But in reality, barter has a lot of problems, right? And some of those problems we can understand as programmers. So the first one I'll put to you, if you barter, if you trade everything, here's two shops, here's a fruit stand and a shoe store. If you have all these items and you need to barter them, you need to set up an n-squared complexity table to describe how you barter, right? How many bananas goes for a pair of slippers and how many mangoes for dress shoes? And then if you extend that to a city, all the things that humans have they might want to sell, you've got this massive complex table, n-squared complexity in how you do the barter. And then on top of that, there's other problems. So you have divisibility constraints. Maybe a pair of shoes is worth a little bit more than 5 mangoes. What do? You throw in a few grapes. What if the guy doesn't want grapes? You've got all these problems of divisibility. And it's hard to move goods across distance too. These two shops happen to be in India, right? And that's a picture of Boston looking over the Charles River. Well, if the fruit shop wants to send his kid to Boston to go to college, he can't send her with a boat of pineapples, right? It doesn't work over space, and it also doesn't work over time. You can't save for the future, can't save for hard times or retirement with pineapples either, right? So barter has all kinds of problems. And so humans always, or virtually always, create money, right? It's a unit of account. We say all these things are worth so much of whatever our unit is. We come up with a unit we all agree on, and it simplifies that n-squared complexity to order in, right? Everything has a price. And people come up with all different forms of money. Gold is a classic example. It's great because it has limited supply. We've been digging it out of the ground for all of recorded history and not consuming it. So we can't change the supply very much in any given year. It's a great form of money. But people have used all kinds of other things. We know they've used shells. That's why in American English, we have like shelling out and clams. We talk about money in terms of shells. There's famous rye stones on Yap Island that they have limited supply because they have to bring them in from 200 or 300 miles away by boat. And of course, we have currency. We have dollar bills issued by the government. That's a form of money, limited supply. We count on the government to limit the supply. And I just have some cans of mackerel there because in prisons, you take away money, people invent new money. They use cigarettes or they use mackerel or salmon, right? People always get a form of money that like sucks humanity in, right? A lot of people spend their life in pursuit of money because it represents all the material goods in the world. Most forms of money meet most of these a set of ideal properties. You need a limited supply, otherwise you get inflation, right? You can't just have a runaway supply of your money. It needs to be divisible, so we get away from that throwing in a few grapes problem. It needs to be durable, so you can hold it over time and use it for a rainy day. It needs to be portable, so you can send your kid to college with it. And it needs to be fungible, where fungible means any one unit can be replaced with another unit. So like 1 ounce of gold is good as another ounce of gold. You know, one $2 bill is as good as another $2 bill for the most part. So that brings us to cryptocurrency. So cryptocurrency is money made by coders, right? This is our money. It was invented in 2008 by somebody we don't know really who their name was, that we know their pseudonym, Satoshi Nakamoto, him or her or they, we don't know. And it's an amazing invention because it combines multiple technologies. It combines cryptography and networking and money theory in a way that's really hard to get your mind around. It's hard to explain cryptocurrency by analogy, so a lot of people struggle with it. You have to learn the pieces and put it all together. So we're going to try to do that some with this presentation. So what I have here to kick it off, the discussion, is an outline of the design of Satoshi Nakamoto back in 2008. He came up with this design. There are like tens of thousands of cryptocurrencies. They don't all use this model. Some don't even have a blockchain, but most use this model, this Bitcoin model. And the idea is there's a shared, they like to use the word ledger, right? Ledger is like an accounting word. You know, you keep track of everybody's account, but it's like a database, right? There's this shared database that everybody or almost everybody has a copy of. And it's organized into a series of blocks. And why that is, we'll get to in a minute, but we've got these series of blocks that form a database that has accounts of who owns how much of the cryptocurrency. In Bitcoin, you know, on there's, you start, if you're processing it, you start with the Genesis block and you process all the way up to the future. And then, you know, everybody who owns everything as an entry in an account, right? And somebody like person A here who has cryptocurrency and wants to send it to somebody else, they already have an entry in this database that says they have Bitcoin or whatever. They put together a data bundle, right, that says, okay, I'm going to move so much of my cryptocurrency over to person B. They put this data bundle in and they digitally sign it with their private key, which we'll touch on in a minute, and they broadcast it over the Bitcoin peer-to-peer network. Okay, and at the same time, a whole bunch of other people do the same thing because there's lots of people wanting to send Bitcoin at any given time. Those get bundled into a block by a special validator. With Bitcoin, that validator is the miner. You hear about Bitcoin mining. It's a person who's bundling up these transactions, as many as possible, up to one megabyte of data, and then doing some special thing with the block, some effort, some work, something that's challenging to get a verified block. Okay, that's what the miner does. And then he broadcasts that over the same Bitcoin peer-to-peer network, and all the nodes on the network, you know, tens of thousands of nodes of wallets and miners and just people who want to run a node, look at that and they make sure all the transactions are legitimate, and they make sure this special validation step that the miner took is legitimate. And if it is, they add it as a new block to the blockchain. And then the process repeats. Okay, so that's the core cryptocurrency model. And what it does is it makes those units of account on the database satisfy those desirable properties of money, right? So it's limited supply. Bitcoin, there's only going to ever be 21 million Bitcoin by design. Okay, so it's limited supply. Divisible. Each Bitcoin, you can have a fraction, you can have up to 1/100 millionth of a Bitcoin. So it's divisible pretty much as you'd want it. It's durable. It exists on this distributed database. It's on tens of thousands of nodes all over the world. I mean, it's the ultimate in redundancy. It's portable because it's just bits, weightless, right? It moves at the speed of light. And it's fungible for the most part. For the most part, one Bitcoin is as good as another Bitcoin. There are exceptions to this, which we'll talk about. You know, the government can step in and say, you know, this address is banned or things like that with Bitcoin. There are other cryptocurrencies that address that concern and hide the source of funds. So cryptocurrency as a whole completely addresses the fungibility, but each type of cryptocurrency addresses it more or less. So what we have then is we've made this new form of money, this amazing thing that just sucks humans right in, right? We get pulled right into money. And that's what's happening here. It's to the point where all the cryptocurrency together, it's worth like $2 trillion, right? People are really, goes up and down with price, of course, but people are really getting sucked in. And here, another important part of cryptocurrency is that it's not one entity driving all of this, right? These nodes, those nodes we were talking about that do the validation and do the mining, they're spread all over the earth, right? Every legal jurisdiction has them. I mean, this is a site that tracks them and makes this map. It's probably, you know, in some cases it's exit nodes from Tor or VPNs, but you can see they're especially prevalent in liberal democracies, but they're existent to some degree everywhere, every continent. So it's unstoppable. It's like this process we were looking at, that process that Satoshi Nakamoto invented, is like a law of nature now. You can't stop it. Yes. They can live in a data center or they can live at home. You need like even the big blockchains have maybe a couple hundred gigabytes of data. You can run one at home on your PC, or you can run it in a data center. Well, that guarantee comes from the process. You're saying, how do you make sure you get them all?
Well, like you mentioned just a moment ago, that governments try various data centers, for example, like right now, they closed off a lot of stuff in Russia, so to speak.
They didn't close off Bitcoin, though.
Well, that's what I mean. You know, the idea is it's built on digital ledgers. That's the base technology from years ago, but it moves around. How does it decide? So data center in California and data center in New York may duplicate one set of Bitcoin, but none of it may make it over to Europe, let's say.
Well, the system enforces that everybody has the same database. I mean, you know, so it's been running for over 10 years now, and how it enforces it.
But it's not every version of Bitcoin.
Are you talking about forks of Bitcoin? Yeah,
Well,
the Bitcoin, core Bitcoin, it has one database. Everybody has a copy of the same database. There may be a little bit of noise as you're adding new blocks and determining which block is added, but the database is identical with all participants.
Basically replicated in all the nodes.
That's right.
The transactions and everything replicated throughout.
Yes. Okay. Yeah. So there's tens of thousands of copies of that blockchain I showed. And there's an incentive for everybody to get synced up with the same one. And it's a system that works. Mm-hmm.
Yeah. By that standard, you're saying, well, if I have a private one, my computer's off.
Yeah, it will automatically sync up. That's right. Yeah. Mining is the process of creating the block. So let me just go back up. This guy who's bundling all these transactions and making a verified block, that's the mining process in a proof of work cryptocurrency like Bitcoin. And I'll talk a little bit more about that, but that's the mining process. And before moving on to a technical discussion on blockchain, I wanted to just add this note on using cryptocurrency. It's good to have a mental model of the core nature of what it is to use cryptocurrency. In the Bitcoin model, there's public key and private key pairs. Okay, so if you have a public key and a private key pair, you need software to generate it. But once you have that, you don't need any software to own Bitcoin or to own the cryptocurrency. Ownership is defined through that pair and that pair alone. So you can take that public key, you can send it out to anybody. It's like your home address, right? People can send you stuff from it. So that public key, people can send you Bitcoin. They can't use it to send your Bitcoin to somebody else. So you take that public key, you send it around, people send you Bitcoin, or you buy it on an exchange and send it to yourself. And then that private key is what will ultimately be needed to digitally sign a transaction to move your cryptocurrency. But you don't have to use that right away. You can take that private key, that very complicated private key that nobody could ever guess. You can write it on a piece of, huh? Well, the private key is actually generated randomly. And then there's a process by which the public key, I mean, it's public key digital signature technology underneath. Well, I'll get to SHA-256. SHA-256 is used for mining. It's not used for signing the transaction, right? The signing the transaction, it uses a digital signature, which is a different technology. But if you take that private key, which is essentially random and very complex, you can write it down on a piece of paper and stash it somewhere, and you own the cryptocurrency that it controls. You can come back, tomorrow or in 2 years and enter that key into software to move your Bitcoin. It's like Stone Age at that point, right? That your ownership is just simply knowledge of that key. It kind of redefines ownership. Yes. Huh? If you forgot it, it's gone. It's lost. Nobody can recover it. Nobody else can get it, and you can't get it. If you send money to a public key and the private key is lost, the cryptocurrency is frozen forever. No way.
It's just space on a hard drive.
No way to retrieve it.
It's space on a hard drive.
You might be able to tell your grandkids, yeah, that was my money once. That's about.
While you're on that topic, what's the current philosophy of school?
Well, that's a very good question. There's lots of different ways to store it. Some people, you can buy a hardware wallet that keeps it, that looks like a USB key, and you can store it there. You can encrypt it with a password, with good encryption, and store it on a computer. The general best practice, though, is to write it down. Either use a hardware wallet that's not on your computer, or write it down on a piece of paper rather than have it on an internet connected computer.
But I always feel like you need to have it in a safe box. You need to have fire.
Yeah. If you had enough money on it, you might want to have 2 copies in case you lost one, right? Well, if it's written down on a piece of paper, you don't need to worry about EMP. Yes.
So let's say you buy it, right? And you have a public key.
You always have a public and a private key. If you're using software, the private key might be hidden inside the software. So there's like this whole huge infrastructure built around this core concept. You go online, there's wallets, there's exchanges, there's all these things, but that's at the core what it's using. So you may have software that has the private key underneath, hidden from you, and uses it for you, or it may expose it to you, but it's always there. If you get this, like the software, some software will give you the private key. If you have that private key, you will always be able to recover your funds. And if you're able to recover your funds without explicit knowledge of that private key, it's because you have a password to software that knows that private key. But it's all at the core, it's just that private key. That's it. Yes. Right. It's lost. It's lost. Those are both good questions. So the question is, how's the supply limited, and what happens if too much gets lost? The supply is limited. It's released as people mine blocks. So that block mining process pays. That's why people do it, and that they pay in brand new Bitcoin. So they're creating Bitcoin, and the payment amount gets cut in half every 4 years. So it's rapidly shrinking, and you can extrapolate that out to the end, and you see there's only 21 million. So it's built into the algorithm that there's only 21 million. And as far as it gets lost and what happens if too much gets lost, one Bitcoin right now, it can be divided into 100 million units. So you can own 1.1765543 blah 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 Bitcoin. Let's say out of that 21 million, all but one Bitcoin in the world were lost. You could still take that one Bitcoin and share it amongst all humanity, right? Through those fractions. So the fact that Bitcoin is lost doesn't actually imperil the use of Bitcoin. In fact, it just makes it more valuable, right? It's almost like a donation to the rest of the Bitcoin community. Yes. Well, usually you can. There's websites that have JavaScript that will create it for you. You need software. I mean, it's not something you can do, with a calculator. You need software to do it, but there's lots of software out there to do it. Websites and hardware wallets, right? Lots to make exactly that pair. I just went to a website when I was putting this presentation together to make those two. Yeah. Don't send money to those. Okay, so now let's talk about a key technology behind most of these cryptocurrencies. Not all, like IOTA is an example that doesn't have a blockchain. But blockchain is a key technology behind most cryptocurrencies. And to understand blockchain, you have to understand cryptographic hashing. Now, if you're used to coding, you're probably familiar with hashing, right? It's a common technique. You take big objects and you boil them down to a semi-unique small representation. It's good for building handy data structures. You can have hash-based maps. You can have hash-based sets. So if in your code, you want to have a set of data and you want to take a new one, and so a new item comes in, you want to see, is this in my set? Well, using hashes is a good way to do it. You store hashes of all the items in your collection, and then the new one comes in, you hash it, and you just see if the hash is in there, right? It makes it all fast. A common way to make a hash for this is to take all your data. Maybe it's an image, maybe it's a string. If you want a 16-bit hash, you chop it up into 16-bit pieces and exclusive order them all together. Okay, now you got something semi-unique, you've shortened down your data, but you don't always even need to do something that sophisticated. Sometimes you can just mask off part of it as the hash. So what's illustrated here is an example of masking rather, to get a traditional hash. All this hash does is it takes the first two and the last two characters in a string, and that's the hash. So like if you take Hamlet's soliloquy there, to be or not to be, blah, 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 it ends in troubles. So that hashes to toes, first two and last two, right? Simple hash. And this could actually be useful, this hash. But there's two things that this traditional hashing does that we don't want and that cryptographic hashing doesn't have. The first is that you can look at the hash and say something about the data that generated. Right? We can look at toes and we know immediately, well, the first two characters are TO and the last two are ES, right? And we can also generate another string. We can engineer another string that gives the same hash. That's called a collision, right? So we can engineer a collision like, I don't know, tomorrow he knows, right? Today she goes. Both of those would hash to the same thing. Well, with cryptographic hashing, you can't do that. The NSA can't find a collision. All the world's computers together can't find a collision. Mankind does not know how to find another string that gives the same hash as that one. Well, if there's a back door, maybe it's possible, but assuming no back door, it can't be done. And I would venture to say that probably there's no back door because cryptocurrency is working, right? That's, I don't know about Vault 11, but I don't think that there's not a known backdoor in any of those three cryptographic hashes there. SHA-256 and RIPE-MD 160 are both used in Bitcoin. And SHA-3, which is also referred to as the Ketchak family, is used in Ethereum and Monero. It's like a next generation. And all of those have not.
You really have to start thinking in the next generation now because they're
SHA-1 is, and SHA-0. And
it's only a matter of time.
it may be only a matter of time. That's true. But SHA-3 is a next generation example, and nobody knows how SHA-256 will be hacked. It hasn't been hacked yet, and even RIPE-MD is 160 bits. It hasn't been hacked, and SHA-256 is 256 bits. But it's a valid point. There's no guarantee that those won't be hacked, and cryptocurrency is relying on it. But one thing I wanted to show you, just because while we're talking about this, so here's RIPE-MD. RIPE-MD takes Hamlet's soliloquy and hashes it into this 160 bits, shown here in hex, right? If we go back to this and we change, you can see the green arrow here, just change that colon to a period. It's the tiniest change in the string. It sends those, if you can see them, it sends those 160 bits completely scattered. There's no relationship between these hashes for that very small change, right? So that's the key to cryptographic hashing. You can't tell anything about what made it, and you can't generate a collision. Now, if you're ever feeling low and it seems like there's no magic left in the world, read up more on cryptographic hashing and all the things that can be applied to, because there's magic there. It's used in all kinds of crazy things. One of those things, the one we're here tonight to talk about, is blockchain. So it's cryptographic hashes that enable blockchain. And here's how it works. So this is, again, the Bitcoin model. We take that whole block. Remember, we were putting that block together with all those transactions. We take those transactions and we start by cryptographically hashing them to make a hash. You can see the block K, and we put that into a block header. We cryptographically hash the block header and put it into the next block header. Then we cryptographically hash that one, put that into the next, cryptographically hash it, and so forth. So we build up a chain of cryptographic hashes, and we combine that with some kind of work or some kind of effort or something special required to make a block. No block can be made easily, okay? With those two pieces, we have a system in place where the past is immutable. You can't change it. And so, for example, let's say this is our latest block on the Bitcoin blockchain, right? And we want to go back to block K and make some change. Let's just say we're playing dirty and we want to move some cryptocurrency that wasn't really moved, okay? What would we have to do? We'd go back to that one. We'd be changing a transaction. So that would change the hash of the transactions. That would change the hash of the block header, which would go into the next one. It would change the hash of that block header, which would go to the next one, change that, and so forth. We would have to change every single block up to the current time to make that change, okay? Well, every block would have to be changed from the one that you altered to. I don't know that each one is a segment of time. Each one takes time, and that's a key element. Each one takes some amount of work, and it takes some amount of time. Okay, so what that? I'm sorry, say that again. They are time stamped. Yes, they are. But I mean, you could fake the timestamp. But what keeps you from from going back and changing that. Okay, making a Bitcoin, mining a Bitcoin block today costs around $250,000. Okay, I mean, that's how much you get paid, so we can assume that's roughly what it costs in capital expenses to buy the computer and electricity, right? So you might say, okay, we can go back. We know we're going to have to change every one, so that's going to be 4 times $250,000. We can do it for $1 million. Okay, recreate these 4 blocks, but the money isn't the problem. The problem is the time it takes to do it. So while we were like spending our $1 million with our warehouse of computers, recreating those blocks, the whole rest of the world was marching forward with the blockchain, getting the mining reward going forward. The whole rest of the world, everybody, all those nodes we saw all over the globe that are miners were mining in the meantime. We don't have enough computing power to match up the rest of the world. So by the time we recreated the 4 blocks, the world's moved ahead by 40 or 400 or 4,000 or however many. It's that combination of cost and money and cost and time that prevents us, combined with the cryptographic hash that can't be reverse engineered, that makes it absolutely impossible to go back and change the past.
So who's paying for all these blockchains to live on all of this?
The block reward is paying. So everybody who, if somebody mines a block, creates a new block, they're paid in new cryptocurrency, and that's the reward for doing it. That's what makes it all work, is that payment to generate a block. That makes sense. So does that make sense? Because that's the blockchain in a nutshell. Hard blocks combined with cryptographic hashing, and that's it. That's the blockchain. Oh yeah, sure. Now, most Bitcoin is mined using ASICs. You need to buy the right computer hardware. You need to buy ASICs to do it efficiently. Well, it's more than just the cost, though, right? You can spend any amount of money, but if you're spending more on electricity than you're making on Bitcoin mining it, it doesn't work. You need ASICs. You need ASICs. So you have to buy ASICs, and what does it? I don't know that it takes a license. You go buy them. Okay, so does that make that's a key juncture, is the blockchain? Does that? Yes. Well, I actually have that in the next slide. Look, see that other data block? I'm going to spread that out into other data and something called a nonce. The other data also includes things like version number and, like overhead, stuff like that. It's just miscellaneous stuff that isn't really relevant. You could put anything in there, and we're going to put a nonce in there at the next slide. But before I do that, actually, let me go back. Any other questions on blockchain? Does blockchain make sense? How it's immutable?
The bigger problem is understanding.
Well, we'll get right, but we'll get to that. Does the blockchain make sense? Any questions on?
The key thing is we're talking about a fraction of some number.
Oh, it is. It's a ledger. It's an entry on a ledger, on this distributed ledger. That's it. It's only worth something to you because it's worth something to somebody else. That's right.
You own a fractional ownership.
Well, I mean, right. It's not nothing. It's not nothing because somebody else wants it.
But not until.
Right. That's true. Right.
It's just a number.
Right.
A fractional ownership of 21 million.
That's all it is. Yeah, it's just a number in a database. Okay, so the piece that we need to explore here, because we talked about, it needs cryptographic hashing and the blocks need to be hard to generate. So the question is, how do we make them hard to generate? Okay, so one way, and it ties back to your question about what is in other data, one of the things that we can have in other data is something called a nonce. And a nonce is something that can take on any value and the block still be valid. You know, it could be random data. It can count 1, 2, 3. It's just a chunk of data. Okay. And it's there only for one purpose. And that purpose is to change the cryptographic hash of the block header. Like we saw, remember with Hamlet's soliloquy, we made one small change and everything changed in the hash, right? So every small change we make to the nonce completely changes the hash. And what we're trying to do, and this is the proof of work mining concept, is we're trying to get a block hash that has a certain number of leading zeros. Now, strictly, it's just that the block hash has to be below a threshold, right? But that one, so it's a little more complicated than leading zeros, but you can think of it as leading zeros. That's actually the way Satoshi Nakamoto in the white paper presented it. You're searching for a certain number of leading zeros. Now, as we discussed, a cryptographic hash can't be like reverse engineered. So the only way to find one with enough leading zeros is to keep changing that nonce and keep hashing over and over and over again till you happen to stumble across one with this many leading zeros. So, and that hash, actually, Satoshi Nakamoto has it as double SHA-256. He saw some reason to make it double. So you hash the block header, and then you take that result and you hash it again, and looking for these zeros.
So you rehash the hash.
You rehash the hash result. That's right. Yeah. Yeah. And it's doing this that has like Bitcoin miners all over the world. There's a picture of one grinding away as we speak, right? They're doing 400 quintillion SHA-256 operations per second, right? You hear people up in arms about all the electricity being consumed. That's it, right? It's like the electricity that goes to countries going into this. And all just trying to get the leading zeros from a double SHA-256 hash. But that is the proof of work, because we know that takes work to find those leading zeros. And that's what makes the blocks hard and makes the blockchain work.
So that's what the thing said. So you're basically looking for that one key value uses a nonce.
Right.
Versus like really something simple like HVAC.
Right. Could be. Could be.
Because here it becomes more permanent. Get that nonce, because that's expire.
Right, the nonce, of course, it needs to match up with the other data in the block header, right? Yeah. Okay, so that's proof of work, but there's other ways to make blocks hard, right? So people are like, oh, we don't want to spend all this electricity. So somebody had the idea, instead of spending so much electricity, what if instead of having people buy computers and buy electricity, we had them buy the cryptocurrency we're selling? And then make them lock it up, right? Just like they have to lock up their dollars when they buy a computer for mining. And then based on how much they've locked up, we pick at random people to make a block. So it was an idea to kind of mimic this proof of work without the actual work. You just need to be online and get picked at random. And a lot of cryptocurrencies use proof of stake, like Ethereum is moving to it, Solana, Cardano, all those, they're all using proof of stake. But there are more ways. There's like a lot of ways to make blocks hard. There's like something called delegated proof of stake. So, people were like, oh, we don't want to run these Bitcoin miners with all this electricity. We just want a proof of stake and be online. And then the next guy is like, yeah, I don't even want to be online all the time, right? Even that's hard work, getting all those nines of uptime. So delegated proof of stake, you take your cryptocurrency and you stake it with a hand, like there's like 100 validators, say in Cosmos, for example, and you can delegate for them to do the mining with proof of stake. There's something called Federated Byzantine Agreement that's really efficient, but some people complain that it's centralized. It's used by like Ripple and Stellar. You've heard of those. Proof of history is a really cool concept used by the cryptocurrency Solana. It just runs runs a cryptographic hashing algorithm on itself over and over again as fast as it can. It turns out making a cryptographic hash and rehashing it is naturally serial, but you can validate it in parallel. You can take big chunks and validate it if you have parallel processing. So they take advantage of that. And that even those three don't do it justice. There's many, many more. And if you can think up a new way to make blocks hard, you can make a new cryptocurrency. Yeah.
So what will be, some of that's, what?
I don't like for mining.
That's,
Oh, nice hash.
yeah.
Is that for Bitcoin? Yes, I've heard of it. Is that
So what?
that for Bitcoin it would be proof of work, and that nice hash is running a. It may connect to a miner that uses an ASIC. That'd be the way you would do it, because you just wouldn't get there with a CPU. You need to connect separate hardware and use that to mine. And you'd be doing that double SHA-256 with Bitcoin. That makes sense. Yeah. Mm-hmm. So that's one key technology. But you can see how these technologies you can tackle, you can understand them, right? It's putting them all together that's a challenge. And if you want to continue studying on this, like a good next thing to study would be digital signatures, right? And we just didn't have time for it in this talk. But let me talk a little bit about code. So all these cryptocurrencies, again, there's tens of thousands of them, right? They're nodes, they're miners, their wallets are all written in some software, right? And that's the underlying code. The most common underlying code is C++, because Satoshi Nakamoto chose C++ for Bitcoin. So everybody who build off that code base, Litecoin and so forth, used it. Monero was a new code base, but it used C++, Stellar and so forth, right? So that's a big one. But C++, it's great, right? It's good for making big things that run fast, but it's a little, it's maybe a little long in the tooth, right? It's got some cobwebs, and there's new C++ class languages out there that people are also using, and one of those is Golang. So Golang was developed by Google. It's a C++ class language. You can make big things that run fast with it, and it's famous for being easy to learn, right? As opposed to C++, right? It's easy to learn. You can get up and running fast with it. That's its strength. So if you were wanting to get into crypto and you are, language agnostic or picking it up again, Golang I think would be a good choice. Another one that's C++ class is Rust. And Rust is often liked by the hardcore tech guys, I know like the guys who are working with elliptic curves and encryption and stuff, they tend to like Rust, the non-C++ ones. It's famous for helping programmers avoid bugs, some of the, like pointer bugs and things you see in C++. It's used with Grin, Polkadot, and Tari. Tari is like an add-on to Monero. JavaScript and, its related languages, Angular and so forth are important. It's important because some of these cryptocurrencies, like Ethereum, have a built-in programming language. You can write a program that runs on the cryptocurrency itself. I'm going to talk about this in the next slide. But if you want to make a complete product, you need to couple that, which is very expensive execution, with some other language, very fast execution for human interface and databases and so forth. So JavaScript is really good for making a complete product. But really, all kinds of languages are used in cryptocurrency. It's such a big and complex space. Some use Java, some use C#, Python, SQL, others. If you have a favorite language, like let's just say it's Ruby, there's somebody's using Ruby for cryptocurrency, right? In fact, you can use that as your filter to see what cryptocurrencies you want to explore. You take your favorite language, do a Google search who's using it, and then you can go work there. But there's another really important programming layer in cryptocurrency, and that's the interpreted code that runs on top of the cryptocurrency. So some like Ethereum, Avalanche, Solana, Tezos, you can put a program into that transaction. Remember we were talking about the transactions that move cryptocurrency. You can put a program into that transaction, and that program gets run on every node. It's not that it's run one place, and the results are confirmed. It's run on every node. Every time somebody wants to validate the blockchain, they have to run your code that you put in there. Okay, and it's a very powerful concept. It's what lets you have smart contracts. Okay, and the king of the smart contract programming language is Solidity. Is the biggest one used by Ethereum. Other people like to use it too. But there are others. There's like Solana uses Rust, and Tezos uses Python. But importantly, all of these, they're actually running bytecode. So what you do is you have a language like Solidity, and you compile it into bytecode that actually runs on the blockchain. So there are often more than one language that can be used to write smart contracts. Like in Ethereum, Solidity is the big one, but Viper is out there too, and there's others. And I think working in this area is especially interesting and different because it's like next level unforgiving of bugs and flaws. Smart contract code really needs to be flawless. I mean, it needs to be flawless in a new way. My background is in like big robots and like some flight systems. When you have big hardware that can kill people, they really ramp up, the coding standards. You have to like check every number before you divide by it. There's all these coding standards to avoid errors and lots of self-tests, but it's not the same, because if you're like programming a big robot, you want it to not make a mistake. You think in terms of nines. I want this to be reliable, 99.99999% of the time, right? You don't ever get to 100%. It's always how many nines. Because if there's something out there that could happen 1 in a trillion times, maybe you don't worry about it, right? Civilization is going to fall into ruin before this thing comes up. But that's not true with smart contracts, because you have intelligent people on the other side trying to exploit your flaws. It's not that you just stumble across them. Some smart guy or gal out there is is finding them and then pushing your code into them, right? Because that's an opportunity to steal money. So it's really interesting and different in that way. I think it's a cool area to work. And I also like to, while we're on the program, talk a little bit about forks. So all these cryptocurrencies, they're practically all open source, right? Nobody's going to trust it, or I don't know of any who's going to trust a closed source cryptocurrency, right? They're open source. You can go on GitHub and clone it, make some modifications, start a new cryptocurrency, new Genesis block, right? Happens all the time. That's how we get tens of thousands of these. And that's a code fork. So for example, Bitcoin, Satoshi invented Bitcoin. It wasn't too long before somebody said, well, 10-minute block time, that's kind of long. Let's do 2-minute block time. And Litecoin was born. It's a major cryptocurrency now, right? Just fork the code base, change 10 to 2, and off it went. Then somebody was like, wow, Litecoin was successful at 2 minutes. Let's try 1-minute block time. That was Feathercoin, right? Somebody made Bitcoin Cash. So then somebody said, oh, there's an opportunity. We'll make Litecoin Cash. That was another fork of Litecoin. A couple of guys were laughing over some Doge meme, right? They liked memes. So they made Dogecoin. It's worth billions of dollars now, right? Just code forked off of Litecoin. Somebody was like, oh, we really need to worry about secrecy. We'll make coin. Somebody said, oh, we need a DAO. We need master nodes. So they forked it to make Dash. And actually, Dash, the original one was a fork of Litecoin, and then they had an update later that they forked up a Bitcoin to make, because Bitcoin had some new improvements. So it has this complex heritage, but that's Dash, right? And then somebody's like, oh, Dash is proof of work. We want proof of stake, so they made PivX. And then there's like forks of PivX. that's the dynamic nature of what's happening out there. All these new cryptocurrencies, anybody who has an idea of how to improve on one can go do it and give it a shot. And sometimes they wind up worth billions of dollars. Right? Sometimes, but not always, a code fork corresponds with a chain fork. So we were talking about the database is this blockchain, right? And we kind of hand waved about how a new one is generated and it's adopted. Sometimes miners create two simultaneous competing next blocks, right? You know, it's going to happen. All these guys are out there looking for those leading zeros. Sometimes two guys are going to find it at the same time, right? Well, most cryptocurrencies have a way to resolve that. Like with Bitcoin, you know, they both go for a while, and then you wind up the master one is the one, the longest chain, or the one more accurately with the most work. And people wind up eventually saying, oh, this one's is out in the lead. We're going to all move over this and abandon the other one. And that's called an orphan, right? Well, sometimes that forking process, people make a code fork and they engineer it so both forks go on and live forever. You know, so Bitcoin forks into Bitcoin and Bitcoin Cash, right? Ethereum into Ethereum and Ethereum Classic. And then sometimes Bitcoin Cash then goes a while and forks into Bitcoin Cash and Bitcoin Satoshi Vision. And what this means when this happens is you have two cryptocurrencies like Bitcoin and Bitcoin Cash that share a common history. You know, so if you owned a Bitcoin in 2013 before the fork, then today you would own one Bitcoin and one Bitcoin Cash. Right? That's how it works. And this happens regularly too. So those are the two kinds of forks if you're coding or thinking of making a new cryptocurrency.
Go all the way back to this one.
To the Genesis block, the first block.
Blockchain still comes back to it.
No. So, like for example, Litecoin did not do a chain fork. It just did a code fork, and it restarted with a new Genesis block.
So that's a separate,
completely separate database.
there is more than a different set of these out there.
Right. Whereas Bitcoin Cash did a code fork, but also did a chain fork. So then there's part of the chain that's shared with Bitcoin. Mm-hmm. Right, or its own life form. Yes, John. It depends on when you got your Bitcoin Cash. If you got it before the fork, you can go sell your Bitcoin Cash and you still have your Bitcoin. Yes. If you bought it after the fork, then there's no shared history. You don't have a Bitcoin. Yeah. Okay. So now I wanted to talk cover a little bit more on it through the lens of a few cryptocurrencies. And I didn't pick these for any particular reason other than to get some variety. So Bitcoin, we've covered a lot of it, launched in 2009, early 2009, C++, proof of work, 10-minute block time. We talked about ASICs. There are lots of like what they call layer 2s being developed on Bitcoin, but some important ones. Lightning Network is one, and there's side chains too, like Liquid. So there continues to be innovation in Bitcoin. It's a good area to work too, not just in like the brand new coins. They're all being innovative. The most recent update to Bitcoin was something called Taproot that lets you hide scripts underneath Bitcoin addresses. It's all like really new and exciting. But one thing I wanted to do here, since I know it's customary in these to show code, right? I want to show some code, but I don't want to show my code. I want to show Satoshi Nakamoto's code. Let me see. No, I'm not. Let's see. How do I think I need to share screen, and then okay. So I got the first release of Bitcoin. Okay, Satoshi Nakamoto's code. It was released in it started running in January of 2009. You know, everybody studies Satoshi, right? They study his writing. He wrote a white paper. They compare it with other academic papers. They look at all his emails, and everybody speculates who he is. You know, was it the CIA? You know, was it the NSA? Well, I think if we're programmers. We know if you really want to know somebody, you have to look at their code, right? You have to. So let's look at Satoshi's code. I got it up here. This is script.cpp, which defined the scripting language that Bitcoin used. And a little bit of background on this before we dig into it. This bundle, you can find it online of the first release. It's about 20,000 lines of code. C++ code. I mean, in name, you know, it's a .cpp file. It's 20,000 lines of code. Satoshi said he'd been working on it for 2 years when he released it. The line endings are for Windows. So Satoshi, surprisingly, was working on a Windows box. And kidding, right? You wouldn't think, would you? So let me just see if I can scroll up a little bit here. So this is his code. And first I'd point out, look at he's definitely old schooling it with the variable names, right? BCH1, all short variable names with letters and numbers and stuff. And he's also old schooling it, by the way, with self-tests. There's no self-tests in the code. But you can see here, it's pretty clean. It's light on comments. Yeah, but it's pretty clean code. And you know, we won't cover too much, but I want to show you that comment. So here's a place where, so he's working on the scripting language, right? And he was working on this OP not equal, and he didn't like it, commented it out there. He had it in for a while, commented it out. And his concern, it's like a byte-wise comparison. His concern was people would be thinking it was a numerical comparison and get confused. So you can see it's too easy to say something and have some quote wise guy pass in a 1 with extra 0 bytes, right? So here's Satoshi, a few things. You can really see his humanity here, right? He's got some code. He's not sure he really wants to take it out or not. You know, we've all been there. He's got to comment it out, right? And he's got a too clever by half comment in there. Some wise guy is going to come in, right? Who's he writing that for? He's writing that for us, right? We're programmers. He's writing it for other programmers who are going to go in and look at his comments, right? It could be, but he probably was anticipating other people laughing too. Well, when they do it in this way. They try to get they're thinking of the other guy. And so my conclusion, looking at this, so here's, 20,000 lines of code in 2 years, right? Somebody in the zone, that's doable, right? I think we could agree that's still doable if you're in the zone. It's clever. He was at the top of his game when he would do it. I think that's a safe bet. Maybe he was, he's old schooling it with the variable names and stuff. Maybe he was in his 30s or 40s. We don't know, but also he had an industry background. This code is too clean for somebody who spent their whole life in academia, in my experience. Academics write code for the results that they can publish in papers, right? It's an industry that we write code for other people, for our fellow programmers who are working in a group. And this was written in that style. He may have had somebody else reviewing it, but I think it was probably one guy. We don't need to bring the CIA into this. Looks like it's one guy. This is my take. So let's go back then. No ASCII art that I know of. Okay. So let's look at number 2 here. I'm not able to advance. Okay, there we go. So this is the second biggest cryptocurrency. So Bitcoin has maybe 40% of the market cap of all cryptocurrency. Ethereum has maybe 20%, so it's maybe half the size of Bitcoin, but it's number 2. And it was made by this guy here, Vitalik Buterin is his name. And he mined some of the Ethereum early, and he's kept it. He's famous for being the second youngest billionaire of all time for that. He led the team that came up with, they changed a lot of stuff. They didn't just make an incremental change to Bitcoin. They made a big change. They went from C++ to Golang, right? From the beginning, their design was to be proof of stake, and they're finally making the move. Like this year, it's anticipated from proof of work to proof of stake. The proof of stake chain is running. They went from 10 minutes to 13 seconds block time, right? Radical change, and they changed the way that blocks are incorporated to do that. We were talking about, if there's an extra block in Bitcoin, it becomes an orphan and abandoned. Well, in Ethereum, it becomes an uncle. There's a way for later blocks to come back and capture that block, and then there's a payoff to the uncle block and to the guy who captured it, so that it's fair payment when there's a really fast block time. The biggest thing, arguably, was the programming language that was built in. That's a general purpose programming language, loops and conditionals and everything. And we know as soon as you have a programming language with loops, you're going to get endless loops, right? So remember, this code runs on every computer on the network. So that's a real problem, right? You can't have somebody where they put out a program with an endless loop, brings the whole system down. So they invented the concept of gas. So if you want to run a program on the Ethereum blockchain, you have to pay for every calculation in your program a certain amount, right? You front this money when you send out your transaction, you front the money, and it starts burning through it as it runs your code. And if it finishes and there's some money left, it sends it back to you. If it gets in an endless loop and burns through all the money, it runs out of gas, it reverts the whole thing back to where it started. You lose your money, but it recovers from the endless loop that way. So they invented that concept too. And these smart contracts then that can run on it enable things like NFTs, non-fungible tokens, that's ownership of digital objects, oracles, DAOs, which is decentralized autonomous organizations, methods for governance, like maybe one of the biggest things that's eventually going to come out of this, new coins, and so forth. And each one of these could be a whole talk. Like, Evie and I, we've been talking about having a talk on NFTs in June. I think that's, and talk about NFTs, right. But NFTs are one of the things enabled by this ability to run code on the blockchain. And a lot of new coins, a lot of cryptocurrencies don't have their own blockchain. They just run on a smart contract on Ethereum. In fact, we could make a new one in a day. We could make it like a Southwest Florida coders coin. Sorry, we could even call them Swiffles, right, or something like that. Literally, it could be done in a day. We could all get together and do it in a day, easy. If you write the coin to something called the ERC20 standard, it's like a standard interface, then your new currency automatically works with existing Ethereum wallets like MetaMask, just out of the gate. It works. And there's a standard for NFTs too, called ERC 721.
So what do you use?
C++, yeah. But I'm not in favor of Golang. It's just, it's hard to give it up. Yeah. Well, if we jump down the list, this is number 20, something called Cosmos. It's also written in Golang. Its big thing, just to touch on some of the variety of what's happening out there, its big thing is it makes a hub to connect other cryptocurrencies. So if you make a cryptocurrency and you add this interface, this IBC interface to it, and they have a SDK to help you do that, then your new cryptocurrency can live in this ecosystem. And you can easily move tokens from one cryptocurrency to another automatically on the blockchain through this hub. It's really cool. You can even do like smart contracts that include multiple chains. And so that's Cosmos. Yeah. Well, right. The exchange rates work out. People are doing it. There's like special coins just to provide liquidity. Osmosis is an example for exchanges on Cosmos. Cosmos is, I mean, the market cap is maybe 8 billion. Yes.
Bitcoin had a limit as far as how many you can mine.
Yes.
Do all of these other coins also have a limit, or different limit, same limit? How does it?
Well, that's a
What is the value?
right. That's a great question. Generally speaking, they're all different. And that's one of the ways that they innovate. Like some of them, like Ethereum, they just from time to time like cut back on it. You know, like the developers. It has no fixed limit. There's limits in how much can be made per day right now, but we don't know exactly how they're going to change that. You know, it's changed in the past. There's some like Monero that, as opposed to Bitcoin keeps getting halved and eventually goes to zero. Monero shrinks until it hits some limit and it just stays at that limit of payment. So it's like there's constant inflation in the future, but by a fixed amount of new Monero every year. And people debate, as you can imagine, what the optimal strategy is. But that release, how the cryptocurrency is released, is like a key property of the cryptocurrency. I'm not listing it up here, but maybe I should have. But it's a very good question. They're all different. You have to look it up. Monero, dropping further down the list now to Monero. Maybe Monero is worth about $3 billion. I'm including it because it's a private cryptocurrency. It's actually the biggest of private cryptocurrencies. All the ones I've talked about so far, Bitcoin, Ethereum, have what's called a transparent blockchain. So you have that public key that's your address, right? That protects you because you can be doing things and nobody knows you own that. But if somebody learns that that's yours, and there's multiple ways to do that, then they know everything in Bitcoin. If they learn your public key is tied to you, they know how much Bitcoin you own. They can look it up. They know when and from where it came, and they know when and to where you spend it, right? So there's times we don't care, about our spend. No, but we don't care if somebody knows we buy broccoli at Publix, right? But there are purchases that we care about. We all care about some. We might care, what political party we're donating money to, or we might have some sensitive purchases. And so private cryptocurrencies address that by hiding in some way the movement of funds. And Monero is the king of the private cryptocurrencies, and it hides the sender and the amount and the recipient in every transaction using cryptographic techniques. Kind of cool. And now the last one, dropping way down the list, okay, it's PIVX. It's 802. I mentioned it earlier as a fork of Dash. PIVX is an optional privacy coin. You can use it privately or you can use it transparently. Yeah, I've looked into it. I would say it has maybe 3 developers, right? It's like that. Maybe a similar size team for marketing. It has a market cap of around $20 million. And I only mention it, not necessarily it in particular, but just like what an example one at 802 looks like. There's over 800 cryptocurrencies that are more valuable than PIVX is. Yeah, this code's on GitHub. Yeah, yes it is. You can fork it. Many people. There's a PIVX Lite, if you can believe it. It's been forked off of PIVX. There's a Veil that's been forked off of PIVX. But one of the things that it does that's pretty cool is it has a treasury built into the cryptocurrency with voting by people who own the cryptocurrency on how that's spent. So you can you can make a proposal. You can say, here's the way I'd like to improve PIVX. You can put it out as part of the protocol, a link to your proposal, and people will vote on it. And then if it gets selected, you'll automatically be paid in the amount you request of PIVX to do that project, right? It's like really cool that way. By the way, PIVX was once upon a time a top 10 coin back in the day. It had a bug, and the bug related to its former privacy algorithm. And when everybody lost their privacy, they didn't lose their PIVX, and they re-implemented it later, and that's when it fell. So it's like a fallen cryptocurrency, right? And so just imagine it's all these hundreds of cryptocurrencies, they all have this complex like heritage, right? Just think of how complex this domain is. So employment, there are like so many places to work in cryptocurrency. You know, I go to a meetup, like a Zcash meetup in Boston, and they're always wanting to hire there, right? So there's all kinds of different areas you can work in cryptocurrency. If you pick one and you master it, you can work at aligned companies. Like there's a company, Blockstream, that supports Bitcoin. Others have it. They're supporting industry. Just think of the exchanges. Just think of the guys who make the Bitcoin ATMs that you see in gas stations, right? All people who make the hardware wallets. There's this huge supporting industry. They need programmers, analysts. You know, we're talking about the transparent blockchain and these trillions of dollars out there moving around. There's people studying it heavily, multiple companies studying it and providing services to exchanges and other private entities and the government. The government's hiring. That's another one. Large companies, you see Apple's trying to hire, Ford is trying to hire. Everybody's interested in cryptocurrency. You can work on small crypto projects. Like we were talking about PIVX, you can go there and propose something to help PIVX and just do it as a gig, right? And PIVX is number 802, try number 736 and see, what they want done. They're all needing work done. Mining, staking, and liquidity. So all of this, there's a financial aspect to this, right? Of people borrowing money against other money and all these things going on, and the mining process of generating blocks and staking. There's companies doing this. They're hiring. And finally, what maybe is like the holy grail here is to make your own cryptocurrency. If you've got an idea, there's all these features, right? It might be a technical feature. It might be, a new way to make blocks hard. It might be a new release program, or it could be a new marketing idea. Like Dogecoin. It didn't really do anything new technically. It just had that cool Doge, right? So lots of areas you can work. And I'd be remiss if I didn't mention the risks. This is some really, really risky stuff. It's very volatile in its pricing. And right before you know it, it can go up or down by a factor of 10. So like Ethereum, in the last downturn, it went down to single digits of its former price. You have to be ready for that. If you're a programmer working here, it's important to you because it's the value of the cryptocurrency that drives you getting paid in your work. So that factors in. You have to consider that risk. They all have competition. Bitcoin has Litecoin, Monero has Zcash, right? Cosmos has Polkadot. These are so easy to make that if one finds new success, a competitor comes along. That's risky. They're all off under attack, right? Under attack all the time. There's something called a 51% attack. If we were talking about with Bitcoin, if you want to go back and change 4 blocks back, you can never catch up again because you don't have as much computing power as the rest of the world. That's true in Bitcoin. If you get down to some small cryptocurrency, you might be able to accumulate as much computing power as everybody else, right? And then you would be able to run past them in that race. That's called a 51% attack, right? There's Sybil and denial of service attacks are common. So you have to worry about attacks. And finally, you have to worry about the government, right? The government really is leery of cryptocurrency, especially the guys in the treasury, those kind of guys. There was actually an executive order that just came out this week where President Biden, everybody was kind of relieved because it was kind of more favorable than what people were worried about. It was doing studies on cryptocurrency. But so there's hope, that there's going to be favorable laws, and you see how it's liberal democracies that are attracting, you saw on that map, most of the attention. We can hope it goes forward positively there, but there's a risk of an adverse law. You have to keep that in mind. And as the final slide, how, if you want to work in this area, how do you? I personally have a model of it takes about 100 hours to learn a new cryptocurrency. You know, pick one out. It's 100 hours, right? That's just my mental model. But the 100 hours in the language of your choice. That's a fair statement, right? Yep, fair statement. The 100 hours can be fun though. There's some really good books. I put up the Bitcoin white paper. Everybody should read Satoshi Nakamoto's Bitcoin white paper. It's only 9 pages. Last page is just references, so it's only 8 pages, and there's a few equations in there. Very accessible. You can just look it up and read it. There's some books, Mastering Bitcoin, Mastering Ethereum, Mastering Monero, that are excellent and technical. As a programmer, you would really enjoy those books. There's a book, The Bitcoin Standard, that talks a little bit more about the money theory part, like what we talked about in the first couple of slides. There's lots of conferences on cryptocurrency. And we're fortunate to be in South Florida because there's a disproportionate number of conferences on cryptocurrency in Miami. For some reason, there's a phenomenon. Miami is attracting cryptocurrency. Like, so next month, there's a really big Bitcoin conference. There'll be tens of thousands of people there. And next month, there's also a Monero conference on Miami Beach, Monerotopia. But other places too, you know, in Boston, they have lots of technical conferences where I am, they're great. And finally, communities, GitHub, you know, is great. Where else can you just go get all the code, right? We can go download it, take a look, see what people are saying about it there. And most coins have a Discord server. You can, you know, get information there. And most have a subreddit. So that's a good place too. And that's it. Yeah. Thanks. Yeah, yeah, we're, yeah. So we could.
Hey, I'm gonna use the microphone. Dogecoin. When I first looked at it, it looked like it had basically it was unlimited, and it seemed like a really bad investment. Was I wrong about that? Or I know it was wrong about it being a bad investment.
Speculating on investment is really hard to do. Dogecoin taps into the meme concept, and it depends on how much you believe in the meme concept, right? Memes are a powerful force. There's no disputing it. And maybe memes will carry things like Dogecoin forward. But, you know, the old school part of us maybe is leery. Any other question? Yeah.
If the blockchain keeps growing, it's a combination of all the transactions that happen.
Right.
Doesn't it get like heavier time, I think, in terms of
Oh,
computing power?
Absolutely. That's a big problem. And that we were talking about like the fork of Bitcoin to Bitcoin and Bitcoin Cash. That whole fork was over a dispute on how big blocks should be. There was a camp that thought it should stay at 1 megabyte because the blockchain would get too big. And there was a camp that thought it should get bigger because computers are just going to get faster and the hard drives bigger, and that'll let more processes go through. So that was actually the issue that caused that fork. Like these big coins, they have blockchains, you know, and there's ways to prune them sometimes too, but have blockchains, if you wanted to download it, you know, it's like hundreds of gigabytes. Like, I don't know, maybe Bitcoin's like on the order of 500 gigabytes. So the question, what people who philosophize on this, what they ask is, okay, is it growing faster than hard drives and bandwidth are growing? If it's growing faster, we're going to have a problem. If it's growing slower than hard drives and bandwidth, we're not ever going to have a problem.
And if I make a transaction, for example, and it's somebody some Bitcoin, then somebody, whatever these nodes, whoever controls it, needs to go back through the blockchain to verify whether if I send a transaction today.
Yes.
And then I want to access my Bitcoin of few. Then
They have to go, they go back and find
They go
that
back and
transaction.
find that transaction
Yes.
to double check that my Bitcoin's mine.
That's right. That's right.
Okay.
And when you first sent that transaction, they had to go back in time to make sure the funds you were drawing it from were legitimate.
Okay, yeah, so it stays forever. and
Stays
this is
forever
like
and has to be
file.
reasoned about forever.
Okay.
That's right. Uh-huh.
So let's see
An arrow. Uh-huh.
so if I was to make my own, how would I do it?
If you wanted to like fork it and make your own,
Yeah, if I was to do that.
well, you could go to GitHub and clone the repository. And then you would need to have some kind of infrastructure to start mining, because you have to bootstrap it, right? But it tends to work because, yeah, you don't have a lot of computers at the beginning, but your cryptocurrency isn't worth a lot at the beginning either. It's like in the early days of Bitcoin, it was just like Satoshi Nakamoto himself. That's how he has so many. He was the only one mining for a while. But nobody did like a 51% attack against him because it wasn't valuable yet. The two tend to go hand in hand. So what you want to do is bootstrap it, clone it, get it started, bootstrap it, start mining yourself, and then try to get other people on board, and hope that your cryptocurrency goes up in value. And as it does, more people come on and want to mine to make money.
At that point, my thing for that.
Well, if nobody knows about it, right, it would start out essentially at no value.
When I would trade it.
Well, if you wanted to trade it, if you had your own blockchain, you would need to go to an exchange and work out a deal with them. What some people do is they go to like some obscure exchange. They say, look, I'll pay you to offer my coin, and I'll promise to buy a certain amount. So you can get it traded that way. Now, instead of making your own blockchain, instead you used Ethereum smart contracts, that ERC20 method to make a coin, then it would mesh right away with other hardware and software like MetaMask, and you could go to something like Uniswap and build up your own exchange using it. It would be easier that way. You wouldn't have to like go cut a deal with anybody. So those are maybe your two. If you want to make a new cryptocurrency, you can make a blockchain, or you can build on top of an existing one.
So where
Well, so a lot of there's a lot of finance going on. One of the big like innovative things with decentralized finance, or DeFi as they call it, is how you build an exchange. So we're used to like with stocks, like if you want to go buy a stock, there's people called market makers who like sit around ready to do the trade, right? That's kind of their job. That doesn't work very well for cryptocurrency because there winds up being higher costs with the trade. So they have this very clever technique, like Uniswap uses it, of people go in and they provide liquidity. And depending on how you provide liquidity in these pools, it sets the exchange rate between two cryptocurrencies. So like you go in and you put in a bunch of cryptocurrency into two pools that can trade based on the ratio. It's the current price ratio. And for doing that, whereas instead of a market maker making money, you're the guy providing the liquidity with this new type of system, and you get paid a certain percentage. And it's really clever and really amazing. The challenge that it's facing, if there is one, is with government regulation. You know, that's maybe in the coming year or two, that's going to be the thing to keep an eye on there. Technically, I think it's fantastic. It's just a threat to entrenched guys. Does that answer your question?
Alrighty, there's a couple of comments in the chat. One was Ben saying a vampire attack earlier earlier when you were talking about attacks. But yeah, just Emily, just wanted to say thank you very much. That was great. And Sven just left a message saying Uniswap is also a great founding story to read up.
Well, good feedback from Sven. Sven gave a great talk a few years ago, by the way,
On blockchain.
programming on Solidity.
Yes.
It was nice to have him there on the call. Yeah.
But yeah, let's hang out here for maybe just 2 more minutes. And I hope everybody can join us. Does everybody know where we're going? Raise your hand if you don't. I know there's some few members. Oh, Mason. Yeah, so you know where downtown House of Pizza is? The little courtyard in downtown Fort Myers? Okay, usually we all meet there in the patio thing. There's like a few restaurants around. You can get pizza or get any food from the other restaurants, but that's usually where we all hang out. And yeah, I guess that's it. And thank you so much, James. That was awesome. Yeah, thank you. And thank you everyone online for staying with us. We have a recording. Bye.
Thanks, James. Thanks, Arella.
Thank you, Chris. Thank you, Sven.